Welcome everyone. Sorry you weren't able to hear me before. I know we're global, so whatever time of day it is, I hope you're having a good day. And glad that you're joining me. A special thanks to Mark Broadbent for, excuse me, for arranging this, for facilitating this meeting. And a little bit about myself. I run my own company back in New York called Sleek Technologies. I'm also a principal consultant with Talon. An MVP for 10 years now in data platform, lots of speaking and writing. Really, I'm just a geek from Brooklyn, New York who loves to write code. That's pretty much it. And those books on the right that Mark was kind enough to mention, the 2012 book there, those are kind of old. All of my newer content you'll find on Pluralsight, including tonight's content and other good Cosmos DB content and SQL Server content as well. So there's my contact info, and with that, we're going to just jump right in. Here's a link. I had it up there. I think you had video but not audio before. So if that's the case, I'm just going to assume that you jotted down this bit.ly link at SQLUK_Cosmos_modeling, and I'll throw it up again if I have to at the end of the session. You'll be able to download a zip file that has all the slides and code. So the objectives are to, well, first of all, get familiar with some of the core Cosmos DB concepts for those of you that are not very familiar with Cosmos DB. We're not going to do a big, too big a picture of it, but just the key things you need to really know about to follow along with the session, and that would be partitioning notably, the most important concept in Cosmos DB. And then we're going to take those core concepts, and we're going to learn how to take an approach to data modeling for Cosmos DB that is going to be very different than what you're used to in relational databases. And many of you, if not most of you, are familiar, hopefully, with the AdventureWorks database or comfortable with, let's say, the Northwind database or these types of relational databases. And this has been something that you've been working with for many years or perhaps decades. And of course, it's very different in the NoSQL world of Cosmos DB. So by the time we're done, you'll understand those key differences and how to apply new ways of doing things, in some ways radically different than the way you've done them before, in order to achieve a good relational data model in Cosmos DB. So the quick 101 for Cosmos DB, it can be defined as Microsoft's NoSQL database that runs on Azure. The key pillars, the core features include global distribution, really just point and click to bring your data closer to your users and get really low latency, single-digit millisecond reads and writes to your users wherever they are in the world. Horizontally partitioned. That's really going to be something we'll be talking a lot about. We won't be getting into global distribution. I'm talking at a high level here, but this horizontal partitioning is what it's all about when it comes to scale, both in terms of storage and throughput. And we're schema free, which means that we don't really have to enforce a schema. There is schema, but it's defined by each individual item. It's not enforced or managed. And it's multi-model, meaning it's actually not just limited to JSON documents that we'll be looking at today, but there's also support for graph data models, and there's also support for columnar and MongoDB compatibility, so as well as Azure Table Storage. So we're going to be focusing, of course, on the core API, which is known as the Sql Api. Just another reason I really want to stop using the term NoSQL, because the main API that we work with in Cosmos DB is known as the Sql API. So let's not call it NoSQL. I really don't like that word anymore. Let's just call it non-relational, right? Which is to address the problem that the term NoSQL was kind of coined for, which was, to achieve virtually limitless scale, and in the case of Cosmos DB, actually limitless scale by horizontal partitioning. So let's just, and we'll define it in those two ways: A, as horizontally scalable, and B, as non-relational. Let's just cover those two really at a high level really quickly before diving in. So when we say horizontally scalable, we have a container in Cosmos DB, and this is one or more containers that you will have in your database. Just maybe like you kind of have one or more tables in your relational database, but not quite the same. But it's just one entity that you interact with. You read and write data to that container. Logically, it's a single resource to us, but behind the scenes, Cosmos DB is managing a cluster of servers, and it will add more servers as needed to accommodate your growth, to accommodate your scale. and there's no upper limit really to how many physical servers there could be in the cluster. So, and you really need to think of each one of these as having their own CPU and their own disk storage with a fixed capacity. But instead of having to worry about building bigger and bigger machines, where at some point you just can't build a bigger machine, the obvious way to scale is to scale out and just add more machines, 1 machine, 10 machines, 100 machines, 1,000 machines, right? And if you do things right in terms of partitioning, you're going to get that unlimited storage, right? As well as the unlimited throughput, because each of these black boxes here, which I've been calling machines, but let's just also call them physical partitions. They're not exactly the same, but they're very, very similar. Just like any box, it has its own CPU for a throughput and its own storage. So in terms of volume and velocity, we can just keep scaling. I hope that the audio is coming through. And I'll just keep going unless I'm interrupted to find out otherwise. All right, so well, the second term I used was non-relational, right? And what do I mean by that? Well, in the relational world, what do we do? What do we have? We have rows. And what is it that we love to do more than anything in this world? We love to join those things, don't we? We just love joining these tables. We love making foreign keys and primary keys and foreign keys and building out that perfect normalized data model that's just very efficient for a transactional workload, and and that's what makes us happy. Well, in the world of NoSQL, or I should say in the world of Cosmos DB, we store data in documents, JSON documents to be specific. And while there's absolutely nothing stopping you from doing the exact same thing, that is, referencing one document from another and doing things very similar to the way you've done them before, the fact is that this would break down. This would not perform very well. It's just not a good design. And the reason why, again, it just ties back into being horizontally partitioned, and that is that any one of those documents could land on a different physical server or a different physical partition, and I'm calling them the same thing. So let me just clarify that each of these black boxes, yes, it's very much just like a box, but it's also a unit of replication for high availability. So each one of those black boxes is replicated 4 times. Each physical partition, there are 4 replicas in any given data center for redundancy. Even if one fails, you have enough for a quorum, for consistency checks and things like that. So if you think about the goals of Cosmos DB and the service level agreement that it provides for very high performance, it's not that it's impossible to enforce constraints between these physical servers, but obviously that would really have a negative impact on performance. And so it's just not reasonable to expect any kind of referential integrity or any kind of joins or any of that sort of thing in this kind of new world of horizontal scale. Well, that will of course lead you to the question, is Cosmos DB therefore then suitable for relational workloads? Like, no joins, no referential integrity. Doesn't sound very good. And of course the answer to that question is yes. Otherwise we would be ending our session right here. Because many, I should change most to many. Not all of the workloads in Cosmos DB are relational. Many of them are event-driven, but many workloads are, right? And we can actually adapt to Cosmos DB for these relational workloads if we start thinking about things differently. It's in some cases a big shift, a big change in a way of thinking to the way we used to think about things before. It's a new approach, and in some cases radically different, and things that you would never, I don't know how many times I can say never, do in the relational world is common practice and a part of the way that we do things in Cosmos DB. So this is, I hope, a diagram that makes everyone feel very comfortable and very familiar, right? This is a subset of AdventureWorks. When I started this, I actually started with AdventureWorks, but it was just too big, and really I could water it down to this. I could water it down to this data model of just 9 tables and still be fairly representative of many of our common patterns, like a one-to-one relationship between customer and addresses, right? There's the primary and foreign key relationship there, a one-to-one between customer and password. So only one customer password per customer, but we don't want it in the same table. So there's a customer ID that's joining those two in kind of a flyweight pattern. Another one-to-many between products and product categories, of course, on the product category ID. And then very often we'll have those many-to-manys, right, with the junction table in between. Because while, let's say in this example, a product can only belong to a single product category, it can be associated with multiple product tags and vice versa. So we'll have that junction table in between that will associate products with tags in a many-to-many relationship. And then we've got sales orders, right? A one-to-many relationship, obviously, between customer and their sales orders, but then a third level deep for each of those orders details, right? This is something that we all feel very comfortable with, and it's a great starting point for that reason. And if you've never worked with Cosmos DB before, your very first instinct may be, and there wouldn't be anything wrong with thinking that way, I have 9 tables, I would create 9 containers. And as I was starting to say, there's really nothing stopping you from doing that. And unfortunately, a lot of people have already done that and have architected solutions like this, and it will work, but it will in fact be the worst possible approach you could take. So tonight we're going to go through 4 versions of this data model, and this is version 1. So I'm not even going to spend too much time on version 1 at all, because we're going to want to graduate from this to something better to start, right? For the reasons I outlined, right? Any joins here are going to be across the are going to have to be performed by us, because Cosmos DB won't join things for us. It won't join these documents together, and there won't be any referential integrity, and it just doesn't look like a good situation. So how are we going to improve it? Let's just jump right into version 2, and we'll have a look at version 1 in a moment in the portal. But let's talk about customers first. Let's just break it down to these 3 tables. I've got one customer with multiple addresses and a single password, right? Okay. And the first step is to translate, if you will, column names in your relational tables into property names. And I've done 2 things here. Well, actually 3, but the third one isn't visible. The first thing I've done is I've camel cased all of the column names, and that's definitely optional, but recommended just to play along nice. And it's the camel case world of JSON documents. Camel case is usually the standard. The second thing I've done, which is not optional, is I have renamed the primary keys to simply ID. And that is required. So every document does have to have, it's schema free other than the fact that it needs to have an ID property. And beyond that, the schema is up to you, okay? So, and the third thing that I've done, which isn't immediately obvious, but in my migration, and you will have access to the code if you download the sample code for the session, that generates this database from AdventureWorks, right? Is I have changed all the IDs to GUIDs in a cascading manner. Right, so what was formerly integers are actually now GUIDs, and we'll talk about why I did that. But meanwhile, I could stop here and say, hey, I do have these foreign keys, but you can see my camera, right? I've got air quotes around foreign keys, but you really can't use the term foreign keys anymore. We'll have to use the word references. I mean, we could leave these references in place where every customer address document has a reference to its parent customer, and that will work, but it will not. How efficient will it be, right? And that's when you have to stop and realize that we're in the world of JSON. We can have arrays. So here in this case, I can embed the addresses inside I can put all of these 3 things inside a single document, can't I? Right? I can just embed those addresses as an array. I'm only showing one address because the slide is only so big, but I could have any number of addresses. Well, not any number, but a reasonable number. And there's the nested password, which is just using the curly braces because it's like that 1-to-1. And just like right away, like you eliminate the need to join once there's no need to join. Once you actually pre-join, everything is pre-joined here for me. So the fact that there are no joins, it doesn't become a problem, at least for this entity. And there's an elimination of foreign keys as well, cleaning up the model. You don't need a foreign key because every child is known by its parent because it's just simply embedded and nested within it. So we could do both ways, and sometimes people will think you should do it one way or the other, like embed or reference. I was just showing both. This is embedded, this is a reference. And when do you do one? When do you do the other? When is it one or the other appropriate? And the answer to that is that you will embed under a few conditions. Well, if it's a one-to-one relationship like that password, it will be very common to embed it. If it's a one-to-few relationship, like between customers and addresses, so in the relational world, there's no such concept. It's either one-to-one or it's one-to-many, and even if many is 2, right? But in this world, we are going to try to see if something can fall into the category of one-to-few. Like it's reasonable to impose an upper number limit, an upper limit on the number of addresses that we're going to support per customer. That's perfectly reasonable. We would certainly never want to limit the number of orders per customer, right? That's definitely one to many, hopefully one to a great many, right? Certainly too much to embed, but the addresses are not. So you have to kind of like, and we'll talk more about how, weighing one to few versus one to many, but one to few is also going to be a very common reason to embed. And that last item is also very important. Also, if they're frequently queried or updated together, that's just just adds more of a reason. Because actually, if they were very frequently queried and updated separately, then you still might not want to embed, depending on the frequency in your access patterns, even if it's a one-to-one, even if it's a one-to-few, if you have very asymmetric patterns accessing those entities. But normally, if it's one-to-one, one-to-few, and like we could say, let's imagine a customer-facing website where the customer can go and view their profile, and then on that page, they could see all the customer information, and then they could see all their list of addresses, and they can access their password on that profile page, and they can make certain changes, and then they could click save. I mean, it's not unreasonable to say that a user profile would include all those things, a customer, their addresses, and their password. So it's, we query for them frequently for that page and update them together as well every time the user clicks save on that page. So we would reference, on the other hand, when it's one-to-many, especially if it's one to an unbounded number, like hopefully sales orders, or in the case of a many-to-many, or like I was calling out, if they're very asymmetric patterns, where they are just really very independently updated and queried, rather than frequently together, then you might also want to reference. All right, so we're going to go with embedding, right? And it'll be very handy for that profile page. Our join problem is solved, at least at the individual customer level, to get their addresses and their related password. And we're going to store that inside of a container. We're going to call that the customer container. We've already reduced three tables to one container, right? And then the question becomes, how do we partition this container? You need to define a partition key for every container that you create. And that's a very important decision. It's important, A, because the wrong decision means you won't scale, and the right decision means you will, and B, you can't change it easily, or you can't really change it at all. But that's a separate discussion, and one we'll talk about hopefully in our next session when we talk about building microservices. But you need to come up with a partition key, and that is going to be some property in your data, or perhaps a composite, some combination of properties. Whatever it is, you could append. You can combine, whatever it is, it needs to be some value in this document that you are going to partition on. And the only way that you're going to know what the right value is if you understand partitioning. So we're going to pivot now from this to a discussion about partitioning, and we're going to come back and it'll be much easier to answer this question. So what is partitioning? Well, it goes back again to this horizontal scale that we get with Cosmos DB. And if we drill in and we look at these physical partitions, and we write to our container, and our documents can land on arbitrarily, as far as we're concerned, on any one of these physical partitions. It is not our concern. So the question then is, how does Cosmos DB know, which physical partition to store and retrieve documents? That is going to be dependent on the logical partitions, and that is what we define. So Cosmos DB manages the physical partitions, and we, the human, the data modeler, we define essentially the logical partitions. And we do that when we create a container. So for example, if I was creating a container in a database, and I would choose the username as the partition key, this would be, now I'm pivoting to a social networking example, like let's say a Facebook type of LinkedIn type scenario. If that were the case, then what would happen is, well, let's first of all forget about the physical partitions, which is very often helpful to do. Sometimes you need to think about them, but it's usually best, like Cosmos, to be worried about that, and let's just think in terms of a logical partitions. It makes our life a little bit easier. Well, if we went with the username, it would mean that all of Andrew's documents and Tim's documents and Mark's and so on, they would all live in their own logical partition. And because we're schema-free, these documents can all be of different types. So we could say that within every logical partition, there's going to be one document for the user, and that user's profile, let's say, then a whole bunch of documents of a completely different type in the same logical partition for that user's posts, and then maybe other documents for that user's likes, other for that user's comments, and all of these would be of different types with different schemas, but they would all share one property in common, and that would be the username partition key. It's important to understand certain constraints, and these have gone up over the years. So in the early days, this was 512K, which was a little on the small side. But there is an upper limit of 2 megabytes. So that'll, a customer with let's say 5 to 10 addresses will comfortably fit in 2 meg, but you can't cram everything in 2 meg. And at the same time, the maximum logical partition size is 20 gig. And that recently went up from 10 gig to 20 gig. And the maximum physical partition size, well, we shouldn't care about that. It's actually 50 gigabytes, which means that technically if you had 2 bloated 20 gigabyte logical partitions, they could sit on the same physical server, but you don't want bloated logical partitions. And we're going to talk a lot more about that. But here's the magic of Cosmos DB, partition splits, the way it grows. So we've written a bunch of documents to a container. Some of them, and each of them have landed in their respective logical partitions based on the partition key, bounded by the blue dashed border. But which physical partition they've landed on is nothing to do with us. And as we continue writing data, that just goes on to a point, but at some point, you're going to get a partition split when you grow to a certain point, and not necessarily when you get to be full in terms of storage. Remember, there's also throughput, and you're provisioning and paying for throughput capacity. So at some point, even before you fill up a physical partition, you're going to get a partition split, meaning a new physical partition will spin up, and roughly half of the logical partitions of one and only one physical partition will migrate over to the other partition, and then life goes on and on and on. And so that's just really the essence of horizontal scale, right? And you can kind of see, hopefully, that you want uniformity. You want good uniformity across your partitions. You want to avoid what are called hot partitions. For example, something like this is definitely something you want to avoid. Okay. That's what we would call a hot partition from a storage perspective. Here, this looks much better, right? And it is from a storage perspective, but from a throughput perspective, it's not necessarily better, because if you've chosen, let's say, the creation date for the partition key in a write-heavy scenario, that is going to give you a hot partition on writes. So all the writes of the day are going to be directed to that one logical partition, meaning you can hit the same physical partition again. That's a hot logical partition. So the way, when you provision throughput for a container, let's say I provisioned 30,000 RUs in this example. Under the covers, that gets divided by however many number of physical partitions there are. So at this moment in time, that would mean each physical partition is getting 10,000 RUs. If you think about it, at least for my writes and possibly even for my reads, I'm squeezing only 10,000 RUs and paying for 30,000, right? So you can see why that's bad. But if you went with the username, hey, that would be a nice distribution, both in terms of storage and throughput. And that's why username is very often a good candidate for a social network scenario. You really need to understand the difference between cross-partition queries and single partition queries. It's a critical concept, but at this point, I think you have enough background that it should be very easy to follow. If we continue with the same scenario and you run a query like this to get all of Mark's documents, well, when the partition key then is known, and when the partition key is known, Cosmos DB can route that query directly to a given logical partition. Therefore, it knows exactly which physical partition that is. And if this query needed to further filter on Mark's documents, that would still be the case, right? Like, I don't want all of Mark's documents, but just his likes, just his posts, just his posts between this date range and that date range. All of those scenarios would be single partition queries, which is always preferred. And if you did something like this, which clearly, obviously, that's going to be in documents spread across a bunch of different users. This is what's called a cross-partition query, because we don't know what the partition key is, and Cosmos DB has no choice, with the help of the client-side SDK, to run a fan-out query, right? If you see the animation, I don't know if it's coming through. The animation makes it look like it's happening serially. The SDK will parallelize this operation to help speed it up, but it's clearly just not desirable to have to visit every physical partition, right? And then, aggregate all those results. Not that you have to do that work. The SDK does that, but every time, if it's a very common query, it's not going to be a good thing. If it's here and there, it's going to be fine. Okay. So now we're back, right? Choosing a partition key for our customers. I can tell at this point I'm just about 10 minutes behind, probably because of our earlier delays. So I just want to give you the heads up on that. So moving along, now we can start better answering the question how to partition the customer container. You need to ask your questions. You need to ask these questions. What are my common access patterns? Yeah, besides the CRUD, obvious CRUD operations, you obviously need to be able to create and edit and update. But for what's the most common query that the customers are going to be running on the website? They're going to want to get their information for that profile page I was describing, right? They're going to want to, the most typical query is going to be select star from C where, on the customer ID. And then that's going to give me all their addresses and their password for that profile page. And that's, let's say, my most common query. And even if I don't need all their addresses, I can pull back less, right? And still, and further improve my query. So that means that the ID itself is actually a good candidate for the partition key. And this is where a lot of people like stop and they go, "Oh, that throws them for a loop," because, and maybe I guess I didn't explain it. Every document in a container is unique in that container based on a composite of the ID property and then whatever property you choose for the partition key, right? So you can actually have two documents in a container with the same ID if the partition key, and that's whatever property you choose, is different. But if you go ahead and choose the ID itself for the partition key, which you can do, well, that gives you global uniqueness of the ID across the container, which I guess is good. It's nice to know that the ID is going to be unique for all customers, no matter what. But it is also going to mean that you're only going to get a single document in every logical partition. So just to be clear, in case I didn't call it out, the blue dash border means a logical partition, and you're only ever going to have one. And it may not seem very efficient because every document is in its own logical partition, but actually it does satisfy our most common query. If we know the customer ID, we just need to get that one document, and then we get everything for the profile page. So we're going to start with that, and then maybe we'll improve on that later. All right, this gets me to our first demo. We're going to query for customers. We're going to flip back on over to the Azure portal. And gee, I guess I don't really know how to easily do a survey, to find out how many of you are familiar with Cosmos DB or how many of you are familiar with notebooks. But notebooks is a very awesome feature recently added to the data portal, to the Azure portal in the Data Explorer for Cosmos DB, which are just basically snippets. These used to be called Jupyter notebooks, Jupyter spelled Jupyter, and everything with a PY usually means it's rooted in Python. And this is a Python code here, but they've recently added support for C# as well, which is very awesome. It's basically code that runs at the server, at the container on Cosmos DB. It's nothing to run locally. And don't worry if you're not familiar with Python. I'm not the biggest Python person either, but we're doing very basic things here, so you'll be able to follow along for sure. And just to set up, I am going to create a couple of very simple functions to pretty print some JSON to show the number of items that were returned and to show the cost. So this is a really important thing. Any operation that you perform in Cosmos DB, you're going to get in the response headers, you're going to get the cost under this key request charge. It'll tell you how many request units were consumed by that request, right? So I'm going to set things up for the version 2, but I told you I would at least give you a peek at what version 1 looks like. We know what it looks like. It looks terrible. It's got 9 containers for 9 tables and technically works. Again, if you download the code, you will get the generator that generates all 4 of these. You'll get the SQL script that first creates the 9 table relational data model from AdventureWorks, and then you'll get the C# code that generates all 4 versions of this database from that relational data model, this one being the worst one. So if I just open any one of these is just going to look like the row from the relational table. So if I look at customer address, except of course for these so-called system properties that begin with an underscore. So if you ignore those, this is essentially the row from the table, and there's the reference to the parent customer, but of course I don't see the customer name here. So this is just the worst one. We're now working with version 2. Because I'm doing a screen share, the portal is sluggish. You shouldn't think it's this sluggish when you're working with it. you see I've got far fewer. I've got 1, 2, 3, 4, 5. Okay, I've brought 9 tables down to 5 containers, essentially by embedding versus referencing where it's appropriate, right? So the sales orders still live in their own container because we're not going to cram them in the customer. But if I look at every customer item in the version 2 of our database, it looks the way I showed on the slide, right? Well, let me find one with more than one address, just because. Oh, come on, really? Somewhere in here. Come on. Well, we're going to find it when we run our queries. Let's flip over to the notebook. Most of them just have one address, but I'm going to flip over to the notebook. Let's query for customers by switching to. So here I'm just setting some variables to point to version 2 of our database, and there are references to the customer container. For now, we're just looking at the customer container, but I also have references to those other 2 containers for the next demo. So the first thing I want to point out, no pun intended, is that anytime you need to read one document and only one document, and you know the ID of that document and the partition key of that document, those 2 things that make a document unique in a container, it's always better to do what's called a point read rather than actually a query. So here I'm actually not running a SQL query. I'm doing a point read, which takes those 2 things, and that's the ID of a particular customer. And because I've partitioned on ID as well, and let me call that out, if you go to the scale and settings of the customer container, you can see that I am partitioned on the ID property itself, okay? So, and again, like I told you, I've converted all the integers to GUIDs, but otherwise this is AdventureWorks data. So let's retrieve that customer. Okay, Amanda Cook. Bad joke, maybe. Amanda Cook is hard to find, but apparently a customer with more than one address is hard to find. And Amanda Cook, you can see, has 2 addresses, and I retrieved it with a point read and the password as well. And what was the cost? 1 RU. That is the absolute cheapest thing anything can cost in Cosmos DB. Nothing can cost less than 1 RU. And anytime you do a point read instead of a query, and your document is not larger than 1K, it's only going to cost you 1 RU. So that's the best, right? I mean, this is the SQL equivalent where you know the ID, right? But you're running a query where you could potentially get back more than one document, so you just get back the first element, you kind of unwrap that list, if you will, but you know there's only one item in it. You get back the same data, so there's the customer ID. That is the customer ID, right? Because and our partition key, but it's the same Amanda Cook, and it's the same 2 addresses, it's the same document, but it costs 2.83 RUs. Now that's close to 3 RUs, which is the cheapest query possible. The cheapest query is never going to be lower than this, maybe 2.81. It's like hovers around 3 is about as cheap as it gets. Okay, so the lesson there is always do a point read when you just need one document and you know its partition key and its ID. And when you're partitioned on the ID, then you just need to know its ID, and then you can do a point read very efficiently. So let's move on to product categories, and we're just going to put these in a lookup list. Basically, we're going to dump them in a container called product categories. This is not something that needs to scale very much. We don't have a ton of categories, maybe, and even documents. I mean, even products. Products, you might have a great many of products, but they all belong under a product category. This is going to be a lookup list with an ID and a name. There could be other metadata we would want about the product category, but at a minimum, we need the ID and the name, right? And then how do we partition that container? So we're going through the same process, right? First, we convert our column names to JSON properties, using camel case and making the primary key ID. And then we decide on embed versus a reference. And we're not going to embed all the products. The products are very big documents. We're just not going to embed all of the products inside of a max 2 megabyte document. So we just, how do we partition this container? The same questions you need to ask. What are my common operations besides the inserts, updates, and deletes? What are my most common queries? Well, the customer-facing website, the user is going to want to see a list of product categories, right? And then maybe pick a category and look at all the products in that category. So that's going to be very common. Basically, they want to see all of them in one go. It's a small lookup list is the point. So what's the pattern here? the pattern here is, all the documents live in one logical partition is what we want. How do we achieve that? It's a little, I don't know how I would call it a hack. Maybe it's not, this is just a technique, but I would say that every document should have a type property anyway, no matter what. The only rule is that there's an ID property. Everything else is, it's the Wild West. You can do anything you want. And it's usually good to conform to some standards that you impose and have a type category, whether you need it or not. But in this case, we kind of need it because what we're going to do is we're going to set the value of the type property to category in every document. And then if we partition on the type property, that's what you wind up with. You wind up with all the documents living in one logical partition. When you just, instead of saying select star without a where clause, you just include what you know a value to be present in every category in the type, and then you get everything back in the where clause, rather, testing on type, and you get everything back in one logical document, in one single partition query against a single logical partition. So let's do a query for product categories, right? Oops, this scroll is a little choppy again from the screen share. So let's run that very same query that I was just showing on the slide. So these are all the documents. Now, ID and name are the only ones we care about, because every document's type is category, as we know. And this is the stuff that Cosmos DB just adds to every one. There's 37 here, so let me just scroll to the bottom of them. This is all 37 categories that we have, all right? We will never have to worry about exceeding 20 gigabytes of product categories, right? So it's fine that they live inside of a single logical partition. I got them at just about 4 RUs, but we don't need all that extra garbage. So very often, not always, but very often it's useful to replace the star with just the properties that you need back. Select star is not quite as bad in this world as it is in the relational world. Actually, sometimes you need it because it's the only way to get back documents exactly the way they are shaped in the container, as opposed to you projecting some different shape. But here I am actually projecting a different shape, which is a subset of just the ID and the name, which is all I need. So here we see a bunch of the, these are the same 37. What I did from AdventureWorks, I combined categories and subcategories, and that's what's separating the comma here. So in AdventureWorks, there's a clothing category and a shorts subcategory, and I just kind of flattened it into a list here of categories, right? But you can see that, oh, actually, did it go up before this? That's strange. Hang on a second. Huh, let me run that again. Very strange. That is not usually the case. Wow, okay. The cost actually went up slightly. I mean, when I say slightly, I mean from 3.97. I've actually seen it go down. Oh, maybe I'm conflating that with another case. Okay, so maybe actually this is, I might be confusing this with another case. Yeah, I think I am. It's actually costing a little bit more to get a little bit less, but that does seem a little weird. Anyway, I'll have to look into that. So let's move on. Product tags, I'm not going to belabor this. It's the same thing as product categories. The only difference is we have a many-to-many relationship between product tags and products, as opposed to product categories where it's just one-to-many. So I'm not going to belabor the same thing we just talked about. It's the same lookup list. We just have a product tag container, and our most common operation is to list all the tags. So it's the same thing. We want everything in the same logical container. So we'll have a type property. This time, every tag document will have the value tag in that type property, and that's going to cluster them, if you will, inside a single logical partition. And when I say where type equal tag, I get all my tags, and I'll never have anywhere near 20 gigabytes worth of these little documents. Right? It's a think of a list of states and provinces, any kind of small lookup list. This is the pattern. So this is where it gets much more interesting. Products, right? Because with products, we have, we're going to first do the same thing. We're going to transpose our column names into property names in camel case and go with the ID property. But we also have that many-to-many relationship, and that's where things get interesting. So the way that we will do this is we will embed an array. It's a combination of embedding and referencing, actually. The way many-to-many relationships are implemented in Cosmos DB in a relational scenario like this is on one side or the other, you have an array of pointers to the other side. So I could have done this with an array of product IDs inside each tag document. But depending on how frequently how frequently things are done, it might be more efficient to do it one way or the other. I've chosen to do it this way. So inside my product document, I have all the IDs for the tags associated with this product, and that's how I get my many relationship implemented. So how do I partition this container? Ask the usual questions. Besides creating and editing, what's my most common operation? Well, the user has already viewed a list of categories and they found something interesting, and now they want to get all the products by that category, right? So that would be our most common query, let's say. And that means we would want, all of our documents in any given category to be in the same logical partition. And if you're thinking that means that the category ID is the logical choice, well, then you would be correct. And that would mean that any such query would yes, if I needed to pull from 2 categories, I would have to visit 2 logical partitions, but I would get all of the products in both categories if I'm just visiting 2 logical partitions. But then we have a bit of a problem. It's not a problem in the relational world. We think we have everything that we need to display this information on the product information, complete product information on the web page, right? That's what we need to show now. And in the relational world, we might think that, hey, I have everything I need. But in this world, we don't, because we're missing the category name and the tag names. And in the relational world, we wouldn't give it a thought because we would just join, right? Those are foreign keys. We would just join on the other tables to get those names, and then we would have the names, and we wouldn't worry about it. But that, we don't have a joins, right? So how do we given this one document, or how do we display complete information? Because really, if I wanted to get all of the products in a given category, I would run this first query like we've been seeing before, now, which on its own is very efficient. It's going to return all the products in a given category as a single partition query. So that's very efficient, and that's true. But then to get the name of the category, since I don't have that GUID ID, I'm going to have to run this one additional query. That's a second query, just to pull the name on that category ID from the product category container. And then here's where it gets really bad. For each product returned by that first query, I would need to run that third query, listing all of the tag IDs in that array in this in clause, just to get the tag names to display. And if this sounds very painful, right? I mean, this is where we pound our fists on the table and say, where are my joins? And so clearly we need, this whole session is about, coming up with different ways to materialize relationships in a non-relational world. And we've seen embedding versus referencing, but when we are referencing, how do we handle the fact that we don't have these joins, right? And that's where denormalization comes into play. And we're going to talk a lot more about that in my next session, which is about microservices, where we'll have a denormalization microservice that is very similar to what I'm showing now. In the relational world, I mean, if it sounds like the opposite of normalization, that's because obviously it is. Very different than the way we do things in the relational world. We work very hard to make sure that we don't duplicate data. We don't want to have multiple copies of some master data lying around. We want foreign keys to that single version of the truth. So we want to avoid any duplication, and we rely on the database's ability to join and aggregate things on demand in our queries, right? Well, in the non-relational world, we strive to denormalize, and that means we want to optimize our data model to ensure that we don't have to run those multiple queries. We won't have to run those multiple queries if all the information that we really need is inside of a single document. And that means denormalizing. That means doing the evil thing in the relational world, which is duplicating data. And I'm looking at a product document where, in addition to the category ID, I am holding a copy of the category name. That's not the master. The master is in the product category container, remember? With possibly other metadata, but at least to display a product on my webpage, I'll need that category name. And that tags property is no longer an array of strings, which were just tag IDs. It's now an array of objects with the tag IDs and a copy of the tag name. That means that every time I create a product, I'm literally duplicating the category name and the tag names at the point of insert. And that's great. I mean, that means I can just run one query and have everything. I can just get this one single document and have everything I need to display the product, but it raises the obvious problem, what happens when somebody changes the category name or a tag name, and it's one of those objects in that array needs to be updated. And that's exactly what we need to do. We need to, look at the product category and product tag containers and kind of push those changes over to the product container. And that's where the change feed comes in. And my next session with this group is all about change feed. So if you're getting a leg up if you're going to come back, and I hope you do. What the change feed is, think of it like a transaction log in the relational world. It's a persistent log of changes. Every Cosmos DB container, exposes this. It is something that will give you all of the changes in real time. You subscribe to this thing. You subscribe to the change feed API, if you will, and all of the changes get pushed to your code in real time. So every time a document enters or gets updated inside the container, it gets emitted through the change feed. And you can essentially listen, as I was describing, by subscribing to the change feed, and the easiest way to do that is with an Azure function. There's Azure Functions, if you're not already familiar, they're these reactive functions. They get triggered by any number of different triggers, and in our case, it's the Cosmos DB trigger. And there's a Cosmos DB trigger on our Azure function that will just watch that change feed and respond in real time. So it's going to be therefore not too difficult to listen to the change feed on the product category and the product tag container, have our Azure function wake up, and let's use the word propagate or cascade the change to all of the product documents that need that copy to be updated. Now, what I'm going to do is, in the interest of time, I'm going to actually use the code that's on the slide. I'm also going to do something in the background here. I'm going to go to the Azure function. Azure functions are consumption-based, and they have a tendency to go to sleep and go cold, and can take a while to start up. So what I'd like to do is wake it up by just stopping and starting it. So I'm going to show you, first of all, the Azure functions. This is slow only because of the screen share. I think it's this one. Come on. Yeah. Yeah. And I will stop it and start it and head on over to functions. And what you'll see here is I actually have 3 functions, but we're only looking at 2 of them at this moment. We're looking at sync product category name and sync product tag name. And we'll look at that third one is actually for version 4, our final data model. We're actually moving on to version 3. So for the version 3, we're getting this denormalization benefit on top of the embedding benefit that we got in version 2. We're actually denormalizing so that we can optimize and get everything for optimize our data model so everything's in a single product document. With the sync product category name, and I'm going to just open that up and just start monitoring it. And just let that, we'll catch there in a moment. And let's move on to version 3 of our data model. All right. If you look at version 3, it actually has the same number of containers as version 2, but it looks like it has this one additional one, and it does. It's the lease container that is used by the change feed processor library. It is not part of our data model. It just needs to be, there's a small container, there's a small, inexpensive container. 400 RUs is usually sufficient, even for production environments. It's just bookmarks so that you don't have to do any of the hard work. So it's, I'm going to now switch to version 3 of our data model, and I'm going to show you that if I know that this is a particular category ID, if I retrieve the first 5 products in the product container in that category, you'll see, like in version 3 of our data model, there's the copy, right? So the category, I'm holding a copy of, you'll see it duplicated in every one of these. I'm only showing the first 5, clothing, shorts. And if you look inside the tags array, in addition to, I didn't come up with very good tag names, but, if the tag name changes, this is a copy of the tag name that's at this ID, right? So all of them have the same information duplicated. So what I'm going to do is I'm going to do a point read, knowing the 2 things I need to do a point read. So what are the 2 things you need to know? The ID and the partition key. Well, the ID is the ID of what I know to be clothing shorts, right? That's clothing shorts. If I actually scroll up, I think it's the next to the last one. Well, no, okay, I scrolled too far. But yeah, it's clothing shorts, right? C7 ending in 9.4 is clothing shorts. So I'm going to read that one. And I know the partition key is always category for all of them because they're all in the same one logical partition. So it's always going to be category. So I really only need to know one thing, which is the ID. Even though I'm not partitioning on the ID, I'm partitioning on the type. And I'm going to then in memory, this line of code here essentially changes the name to fun shorts in memory, and this updates it in place. I'm going to go hit run on that and then switch right back over here and see if anything comes up. Yep, detected change in one product category document. Oh, look at all the documents that updated, more than 5, 7 actually. I'm going to look at the code that did that in a moment. But meanwhile, if I come back to my container and I run the same top 5 query I ran before, look at every copy has been updated. Clothing shorts is now clothing fun shorts in this product and in this product and so on. So now that kind of solves that problem. And here's the code that made that happen. So if you just take a public method and you decorate it with a function name attribute, it becomes an Azure function. It's as simple as that. That needs to be triggered, as I said, by one of any number of triggers. And we're using the Cosmos DB trigger, which looks at the product category container in the web store database. That should actually be web store v3. And here, don't get confused, collection is just the old name for container. People still throw it around, but we should be calling it container, unless you're working with the Mongodb API. And the Cosmos DB connection string is stored in configuration with my credentials to access this container, and that's the name of the lease container. Again, we don't need to worry about the lease container, we just need to create it. We can name it anything we want. It's very common to just name it lease. But that's just a declarative attribute. In terms of, the parameters handed to us, it's just these two, which are the only two that we need. We need a read-only list of documents that have changed and a logger that we can, write, log output to. Now, one of the huge benefits of the change feed processor library, which is running under the covers when you're using this Azure function, is it scales for you automatically. So if there was just one change here or there, spurious change here and there, this will fire and you're just going to get one document in that array. If there's a burst of 10 changes, you might just get, this fire up and you'll get all 10 in that read-only list. But if you're getting hit very hard with lots of writes, Cosmos DB will scale out. It will multi-thread, and you'll get bits and pieces that have already been broken up by Cosmos DB. All you need to do is process them, and you're guaranteed you're getting the changes in the order that they occurred within a logical partition, which I'll talk more about in my next session. But meanwhile, the short of it is the documents list is a list of changed documents where all I need to do, write some output and iterate each one and get the category ID and the category name and call update product category name. And in this case, there's no such thing as a DML operation like with a where clause to update all the documents that fit a certain where clause. You have to actually retrieve them with a query like so. I'm retrieving all of the documents inside of that product category, right? So this is a very efficient query. It's going to retrieve all the products in a given category, and that's all of them in one logical partition. It is then going to set options that identify the partition key, the known partition key, which is the category ID, and then is going to just loop through this iterator and read each document as long as there are more results. This line of code changes the category name in memory, and this replaces it in the document. I'm good. I'm not, in the interest of time, I'm not going to show you the version for the product tag because it's very similar, but it's a little bit more. Okay, I will show you because it'll only take a moment and it's kind of important. I have the code right here. I actually don't. I have to open the other solution. Sorry about that. Let me do that in the background while I move on. I'll come back and show you. Yeah, go with that. We're coming close to the end here. We have our last piece, and then we're done. The sales orders, and then we'll kind of like tie it all together and give it a wrap. I think I'll just show you that now because it's not going to take very long to load. This is the actual full code that you're going to get in the zip file with the download link. Data modeling, web store Azure Functions. Version 3 of our data model. I just went through the code for when a product category changes, but when a product tag changes, and that was that other function. Remember I said, there are these two functions here. We just saw sync product category name, but there's also sync product tag name. While that refreshes, we'll just go to the code for it. So I just walked through version 3. I just walked you through this code essentially on the slides. And this updates the product category name. But here's this other function that's watching the product tag container. It's very similar, right? Except it's the tag ID and the tag name. But now I need to update all the documents in the product container where inside that tags array, there's an object with a matching ID. And then I need to update just that item in the array without disturbing the rest of the array. So when I call update product tag name, first of all, to find all the documents, that is a cross-partition query, unlike the other case. Because in the other case was all the products within one category. In this case, it's all the products that have a certain tag. And that will be a cross-partition query. So this is an array contains saying if the tags array has an object that matches on the ID, and that's going to have to be a cross-partition query. In the last example, our options included a partition key. But in this example, in this case rather, because it's a cross-partition query, I can't supply a partition key. Instead, I set max concurrency to -1 to tell the .NET SDK to be as smart as it can to spin up multiple threads to speed up the cross-partition query. Now, does that mean it's awful and terrible? No, cross-partition queries in and of themselves are not evil. Depends on how often they happen. The occasional cross-partition query here and there is fine. How often are tag names really changing, once they've been set? I mean, if it's very, very, very often, then this might be an issue. But if it's not, then it's certainly not an issue. To run this cross-partition query and get all the products, and then in terms of making the change to the document, I need to get the one tag inside that tags array, right? So I'm just casting the tags array as an enumerable of dynamic types, and I'm getting the first one whose ID matches the ID of the tag that changed, change the tag name of just that one object in the array, and then replace the document, and that's pretty much the same. So in our last case, we want to do sales orders. You should know the drill by now. Step 1, transpose column names to property names with camel case. Step 2, decide embed versus reference. And in this case, details is certainly a good candidate for embedding. Will comfortably fit in order with all its details inside 2 meg. And so we'll do embedding there, and then we'll put that in the sales order container, ask the usual questions besides creating. What are the common queries? Well, let's say there's 2 common queries here. Certainly, the customer is going to want to see all their sales orders. And let's say kind of not on the customer-facing website, but maybe in a back office somewhere. Some dashboard or some exec wants to see the best customers, right? So typical, account query that descending by count. But let's take these 2 separately. First, the customer-facing query, right? Customer wants to get all their sales orders. Well, that would mean that we would want all of the orders for customers to live in the same logical partition. So if you're thinking that the customer ID is a good candidate, you'd be thinking right again, you'd be correct. But now let's just put the slam on the brakes now. This is not the first time we've chosen to partition on the customer ID. Remember the customer container, the one we chose to partition on the ID property itself because we put the customer ID value inside that ID property. Well, we're also partitioning that container on the same value. And so you need to kind of like move away from the way of thinking like separate containers for each type, when you don't create multiple containers per type. You create multiple containers when you have different throughput needs and partitioning needs. And in this case, these two containers have the same partition. These two entities have the same partitioning needs. The customer needs to be partitioned on the customer ID, and so do the sales orders. So what we'll do is we'll not create that sales order container after all. Oh, I'm ahead of myself. Cosmos DB is schema free, so there's no reason you can't have two documents of different types in the same container. And it's actually you should be doing that when they share similar partitioning needs, as is this case. So we would just need to make a little minor change here. We have a slight little problem in that if you look at the customer container, the ID is the customer ID and it's the partition key. And if you look at the sales order document, the ID is the sales order ID, and the foreign key reference to the customer ID is in a property called customer ID. So to kind of fix this, we will, that's what I was just saying. I got to know how to line up with my slides better, right? So those things don't really line up, right? That doesn't seem quite right. We'll just tweak our customer document, add a customer ID property, and store a copy. So with two copies of that customer ID property in that same document. Another bit of denormalization, another kind of thing that goes against the grain if you're coming from a relational database background. But we don't think twice about duplicating data when it helps us in Cosmos DB to optimize our data model in this manner. So at this point, now here I say you must use a GUID, and here we're tying into why I used a GUID. Yeah, you didn't actually must use a GUID, but you can understand why I did use a GUID as one solution to a potential problem of conflicts. If I take rows from AdventureWorks, from the customer table and the sales order table, clearly we could collide on ID. Making them a GUID solves that problem. Not that a GUID is always the best choice. I could have solved it by assigning a unique prefix on each one as well, like C- for customer, and kept the integer IDs. So I went with a GUID, but you don't have to. And yeah, here again, best practice, add that type property. You don't technically need it. Without it, you could infer by the absence or presence of, like if there's an email address property, I could say, well, then I know that then I know that it's a sales order. Otherwise, I know it's a customer document, but that's really very poor approach, very brittle. What if you one day added an email address for whatever reason to this document? You don't want that. Go with that type property and have a kind of very deterministic way of distinguishing between different types in this NoSQL, in this schema-free world. And that means that we have documents of different types in one logical partition, right? There is one customer document and multiple sales orders. And now we can get all the sales order for a customer with this simple query. And if you think about it, we've solved the problem of our joins, haven't we? They are kind of, it's not going to join them for us, but it's just as efficient. It's a single query will get us a customer and their sales orders from a single logical partition. Let's see that in a demo. So if I want to, now I'm in version 4 of our data model. And I will, knowing this customer ID, I only want their sales orders. Come on. Come on. That's better. I know it was a little fluky there. All right, what did I get? I got back 2 documents. Let's see, I got back 2 documents, and the cost is 2.97 RUs. What are the 2 documents? The first sales order and the second. And each order has the details embedded, so that join problem was solved. And it costs 2.97. Now, if I leave out the type check, and this really is hacky, but I still order by type, knowing that the C in customer comes before the S in sales order, it means I'm going to get the customer and their orders, and the customer will always be first. So now I'm getting back 3 documents. Look at the first one. The first one is the customer type, which is all the customer information, plus the embedded 1-to-few addresses. That's all included with the password, all included in that one customer document, plus these 2 other documents that are the sales orders. They're completely different types, but they have all of the nested details as well. So you're getting all this payload, kind of all pre-joined, if you will, in 3 documents at a cost of only 2.9 RUs. What was the cost for it? Yeah, this was that case. This is what I was conflating before. So I only got back 2 documents and it cost 2.97 RUs. And here I'm actually getting back 3 documents. I'm getting a larger payload and it's costing slightly less because of the absence of the type. The type check is obviously more expensive than adding a 3rd document. But you can see here that things are much more efficient at this point. Actually, we're up in WebStorm v4 at this point. So that takes us to our final query. That back office operation. We want to get orders descending. We want to get customers descending by their order count. So again, in the relational world, this would be a piece of cake. You would select from the order table, group by customer ID, sort by count descending, and you wouldn't blink. You wouldn't think twice about it. But we can't do that here in this world. So the answer again is to denormalize, and in this case, duplicating not data, but the state of data, keeping a copy of the count. If there are 3 sales order documents, I'm going to have a property in the customer document that has the number 3 in it. And that means that I need to, any time there's a new sales order for a customer, I need to update that customer. I need to increment that property value. Isn't that right? And if you're thinking change feed, you'd be right, but there's actually a better way that I'm going to show you, and that is using a stored procedure. Because while change feed will work, it is out of band. You saw that, right? I made the change. We had to kind of wait a few seconds, and it runs out of band with your application, and there could be some time till it propagates. But in this particular case, if the documents that you want to update live in the same logical partition, a stored procedure will be a better choice. And this stored procedure, so when I want to create a new sales order, I will not write it to the container directly. I will instead pass it as a parameter to this stored procedure, which internally will, I'm not going to dig into this. It's really just doing 3 main operations. The read operation, because this is the JavaScript equivalent of the .NET code we were looking at, but it's very ugly. It still calls things collections. It still uses self links from the old days of Cosmos when it was DocumentDB. It's just not important. We need to get a reference to the customer document that we need to update to increment that value, and that's what that's all about. So I'm going to read the customer document. I'm going to increment the sales order count in memory, and then I'm going to write it back to the container so that now it's been persisted. And then I'm going to create the sales order document. And these are nested because it's just the nature of the callbacks, but that's the order in which these things happen. But the beauty is that this is all transactional. With a stored procedure, you are guaranteed that if there's a problem creating this document, creating that sales order, that this replace operation will roll back, even though you've already incremented and persisted the change, which is a very nice thing to have in a NoSQL database, a unique feature of Cosmos DB. But again, it's only when your changes are scoped to a single logical partition. So once you have that in place, your query, that's your query, right? It's just you order by that sales order count descending because it's always going to be updated, right? So let's wrap up with that last query. You can see here in WebStore v4, I'm down to just 3 containers because the least container doesn't count. Because many of you may have already figured out on your own that can't product category and product tag be combined? Of course they can. They're very small. So I combine them into a product meta container in version 4, which has both categories and tags, I think, and just as, yeah, you see the mix of categories and tags. And that's that 3rd Azure function that I was told you I was going to show you before the end. That 3rd Azure function, this one here, sync product meta. So for v4, there's just 1 container. So we don't need 2 functions like we had before, one for the product category name and one for the product tag name. We just have that one. So for v4, it's not 2 functions, but 1, because I'm only looking at the meta container. And inside, for each document, I need to see, well, are you a category or are you a tag that changed? And it's easy to do that by using the dynamic type. And because you don't know the shape of the object. And then, but the rest is the same. Update product category name and update product tag name are the same. So going back to our back office query for our best customers, let's run that query now. So in v4 as well, if you look at every customer document, you'll see the sales order count. This guy has 2 sales orders. So here we go. Let's look at our top 10 customers by doing sales order count descending. Ooh, we got an error. Why? Because this is a cross-partition query. Again, not evil, because if it happens here and there, when every time the exec wants to see the dashboard and see their top 10 customers, it's not quite like a high volume and a high velocity of activity coming from your customer base on the website. But you still need to tell the Python SDK that you understand you are running a cross-partition query. You have to make your intent clear. Yes, I want to run a cross-partition query, please, and don't throw an exception. Because of course I'm getting all customers across all logical partitions, ordering by sales order count descending. Clearly that's a cross-partition query. And Mason Roberts and Dalton Perez, they appear to be tied at 28 each, followed by 27. And a little further down, the numbers go, I think they all say 27. Yeah, but then they'll continue going down and so on, right? So here we go. I want to create a new order. For this customer, that's Dalton Perez. I know that to be Dalton Perez's ID. So this is their new order. It looks like a sales order. It has those 2 details in it. I've set it up to look just like a sales order, right? But instead of inserting it into the container, what am I doing? I'm calling execute stored procedure on the scripts of that customer container. That's the name of the stored procedure. I have to supply the partition key and as a parameter, the order. That may look a bit expensive there. It's about 10 RUs for each write. And that's because of the number of replicas and the indexing policy and all sorts of other things, but it's mostly expensive because of the write, the multiple writes. But you can see that when I run the same top 10 query now, Dalton Perez now takes the lead at 29. And that was transactional, right? So that 28 got incremented to 29 in this document. At the same time, the 29th order got inserted, and you can have the confidence that you won't have stale data, orphaned data, or integrity problems when you use a stored procedure. And that brings us to the end, or does it? Well, it does. I mean, you could take this further if you wanted to. You could create a single container. It's not to blow your mind here, but I can use a single container and put all of this stuff into a single container. Partition on a property called PK, because you can just have a property called PK, and then put inside that PK property whatever partition key value I've been using for all of these other customer ID, the category ID, the type, whatever it is. And people do that, but that is a bit over engineering, I would say. And really, you need to think about your throughput needs. So when you have varying throughput needs, it's good to have separate containers so that you can provision higher throughput for some and lower for others. Even though there's what we have today something called database provision throughput, but it's really better, to provision throughput at the container level in most cases. So with that, right, so our final design was, of course, combining product tag and product category into the single product meta container, as well as using a stored procedure to denormalize the sales order count in each each customer document. The key takeaways for today, I hope that you will remember, is that you need to know what your most common use cases are, what your most common queries are, what your most common access patterns are, and design for those. Partitioning is clearly critical. It's crucial. If you don't partition right, you're not going to get that limitless scale. But if you do, it will be limitless. And you get the best performance. And how do we materialize relationships in a non-relational world? Embedding versus referencing, denormalizing, pre-aggregating, storing related entities in the same container. And we can denormalize data either by using the change feed, which we'll see a lot more of in my next session, or using stored procedures, which is really nice because of the transactional benefits that you get. And you get that ACID guarantee on transactions inside of a stored procedure. I want to thank you. I want to thank Mark. I apologize for going a bit over. I know we got a late start, but I still think I went a little bit over beyond. So thanks for sticking with me.
Thank you very much for that, Lenny. Are you still okay for questions?
I am absolutely okay for questions.
Excellent. So for those people that don't want to stick around for questions, it's worth saying that your next session, Lenny, is on July the 7th at the same time. So definitely register for that one, because I can see change feed being a real boon for a lot of companies to go to Cosmos. Anyway, let's move straight on to the questions. So the first question, would your partition key choice be the same regardless of Cosmos API chosen?
The answer is yes.
Okay.
So the short answer is yes. To elaborate slightly, you have the core layer of Cosmos DB, the core capabilities, which includes this persistence layer, which is something known as ARS. You don't need to know about it, but it's there. It is API agnostic. So if you go with one API or another, your data is persisted, globally distributed, partitioned exactly the same, whether it's a graph. If you go with the Gremlin API for a graph data model, you're still going to have to choose a partition key, and you'll still take the same considerations in mind, but you're dealing with the vertices and edges rather than schema-free hierarchical schema-free documents. But yes, regardless, you're going to get the same benefits of partitioning with any API, not just a SQL API. But you won't be able to do the embedding if you go with Gremlin or Table.
Okay, cool. This, you might think this is a silly question. This is actually the one that I've been. You've not heard my question yet. So, in your Pluralsight course, I'm sure that you kind of allude to this. However, I subsequently asked Microsoft about whether they planned to allow you to switch the API model. I know that there'll be a very rare use cases for doing so, and I also know that you can query. I think you can query graph, can't you, using the SQL API?
I can speak to that. Sure, I can actually, if you just give me half a moment, I can show it visually a lot better. Because of what I just said, right? I just made a declaration that regardless of which API you choose, the persistence layer is the same. So that means that in theory, at least, you ought to be able to freely switch between APIs. Let me just get the slides I'm looking for. We were just looking at the SQL API, and we were working with JSON documents, and we were working with SQL queries, right? That's what we were doing all this session. But there's also the MongoDB API, which is really very similar in terms of the types of documents. They're called BSON, but they're also, you can embed their hierarchical JSON, but you don't run SQL queries. You run MongoDB queries. If you're a MongoDB person, you know how to do that, because this is a compatibility layer for MongoDB. If you're going with the table API, it's key value, which is very much like a JSON document that's flat, like no complex types, no nested objects, no nested arrays, just scalar properties. You can think of, so that's what that table storage is. The Gremlin API gives you a graph, which is vertices and edges, or entities and relationships in plain English. And the Cassandra API, like the MongoDB API, gives you, wire level compatibility with Cassandra. But again, under the covers, it's ARS, Atom Record Sequence. And it's, so when you look at a JSON document, don't think of it that being persisted like a text file on your hard drive where you have a JSON file sitting as a text document. It's just being projected out as JSON for the SQL API, but it's being projected out as a graph for the Gremlin API, which really means that there's, in theory at least, you should be able to freely switch between these APIs, but the reality is you can't. When you create a new account, you get a drop down and you can only pick one. And once you pick that, you can't, that's it. All the databases you create under that account are going to be stuck to that API. So in the early days, there was talk that this would become a reality one day. And that is looking less likely to happen. The reason being the demand, the customer demand, because really, why would you want to do that? And we're going to talk about the one edge case that you started mentioning with the Gremlin in a moment. But that aside, I mean, really, if you've done your analysis and you've chosen an API, you've gone with the MongoDB API because of the reasons that you would, which would be like you inherited an existing MongoDB application that you're now migrating to run in the cloud with Azure, with Cosmos DB as a backend, but you don't want to re-engineer your application. It's still MongoDB. That's a good reason to go with it. And if you go with it for that reason, that's it. You made your decision. You would never want or need to switch. The one exception is a unique case is the Gremlin API. Yeah. So if you create an account and you choose the Gremlin API, you will have interoperability with the SQL API. You will be able to use the SQL API to manipulate the Gremlin API. To be clear, the SQL API would be your first choice to go with for a greenfield application, unless it was very graph oriented, and then you might want to go with Gremlin. But when it's greenfield and you don't have an existing investment or interest in MongoDB, Azure Table Storage, or Cassandra, you would never go with those APIs.
Yeah.
Right. You go with the SQL API, or you would go with the Gremlin API if it was very graph oriented. But even if you did that, you would have, all the SQL API, many of the SQL API advantages, including stored procedures. Like that stored procedure feature I showed, only available for the SQL API, but you can still use stored procedures to manipulate your graph because of this interoperability. But if you look at the NuGet package that you install, you can see that other than the SQL API and the table API, they're all third party, right? They're the same NuGet packages you would use if you were going against Cassandra or Table or MongoDB or Gremlin natively.
Okay, cool. Thank you very much for that. Next question. So because schema is not enforced in Cosmos and NoSQL databases, over time you're going to, potentially could end up with various JSON properties. So an example could be, I don't know, surname and last name properties being used for actually the same thing. So your code is going to have to accommodate those kind of changes. Is there any techniques that you can do? Sure. So?
Yeah, let me show you. I got something ready to show for that. Let's go back to the portal. I've got a notebook here that shows exactly that for projections. Well, first of all, the best practices, remember, you know how in best practices I said you should always have a type property? Arguably, you should also have a version property. Because there are no rules, it's so easy for chaos to ensue, as you're alluding to by your question. Maybe it's surname, maybe it's this. Cosmos doesn't care, it'll accept anything. Well, you have to be a little bit more diligent. And one way that you can do it, you the developer that is, or the team, one way that you can do that is by attaching a version property. So if for whatever reason last name gets changed to surname because there was a reason for it, or you added a new property that the older versions of the document don't have that property, whatever it is, it'd be also helpful to always have a version property and increment it so that you can deterministically rely on the absence or presence of a property. But otherwise, and I'm going to clear these outputs because it's just very, very large. But otherwise, let me scroll down. Projections. Yeah. It's somewhere in here. I don't know if I can do a find. Oh, geez. Well, there's the ternary operator. Oh, here it is, found it. I don't know, maybe the property is called given name, or maybe it's called first name. Some documents have it called given name. So what you can do is you can use the coalesce operator, because you can then keep coalescing to other possibilities. But this property, this query here is going to project the property out of this query as child name in all cases, whether it was given name or first name. But it's very hacky. I mean, you can also use the there's also a function called is defined, and you can you can put something like that, and it'll tell you if that property is there. Not the same as telling you if it's there but null. It's actually, is it there or not? Yeah. But again, those are brittle assumptions. It's better to just go with that version property. And this also becomes an issue. So I'd be remiss if I didn't call out the very big announcement about Azure Synapse link and near real-time analytics and Synapse analytics over operational data in Cosmos DB with no impact on your operational data and less than 5 minutes of lag. But of course, in the Synapse analytics world, there's schema around everything, so you have the same challenge. You're going to have to map some schema on the analytics side against the Wild West world of Cosmos DB, where it's schema free.
Do you foresee companies having their own kind of MDS, master data services, kind of processes from, you know, periodically to just tidy up schema and data?
That's an interesting thought. I mean, I suppose there's any number of ways of going about it, but you know, it really depends on what you're modeling. You know, we'll see in the next session. It doesn't always need to be a relational scenario. It could be an event-based scenario. So imagine a shopping cart where, you know, you never have updates and deletes, even as the user is updating and deleting items in their cart, because you're just recording events. So the user adds an item, it's an insert. They add a second item, it's a second insert. And if they change the quantity on that first item, it's not an update, it's a third insert that represents the update of that item. Okay. And those schemas are consumed over a very short duration, right? If the schema changes, it almost doesn't matter, because the value in querying that type of data, let's say IoT telemetry data or sensor data, the value and those schemas change very frequently, right? Sensor data, wow, right? But it's only really ever consumed in the short term. Its value is always like while the plane is in the air, you know, while the elevators are operating, you know, while the delivery truck is out, you know, did the engine break down? And so you know, it's a very different scenario in terms of schema drift.
Cool. I suppose you need to have developers that aren't, you know, just bashing out code willy-nilly and in an ad hoc fashion, I guess, and working to
you'll need to impose discipline. I mean, the example I showed with the stored procedure, right? You can rely on the transaction that if the insert of the new sales order document fails, you can rely that the update of the customer document will roll back. But you can't enforce developers from like in SQL. You can say you cannot write to this table. You have to call the stored procedure. In this world, if a developer goes ahead and just writes a document to the sales order container, then you're going to be out of sync. And you know, you have to have a lot more discipline in this world. A lot of people think that all the problems that are solved by making things easy just go away, and they don't really go away. They just kind of get shifted. Right. You know, things are easier in this respect, but now they're harder in that. You know, as a result.
Cool. Okay. In the interest of time, I want to sort of I've got 4 questions that I really do want to ask you, but we'll try and keep these ones brief. So First question is, I noticed that Notebooks is still in preview. Is there a date that it's expected to come out of preview? Also, it looks like you can only enable it on account creation.
That's right. It's actually it's full featured. So it's the only reason it's not GA is because it hasn't been deployed to all regions.
Right. Okay. Got you. Okay. Next question is I seem to remember not too long ago there being a Spark option, and that seems to now have disappeared off the Cosmos account creation.
Yeah. So check out the new Synapse link.
Right.
Yeah.
Is that private preview now? Is it or
it is? Is it still in preview? Yes, I think so. Well, Synapse Workspace is still in preview.
Right.
But I don't know about the Synapse link on the Cosmos side.
Okay.
Next question.
Cool. So you briefly mentioned indexing policy. I know that Cosmos has its auto indexing policy by default. Is it worth defining your own?
It depends on your scenario. If you have very large documents, you pay for the price on the writes, right? And you enjoy the benefits on the reads, like in a relational database. But the penalty is not as big in this world for indexing everything as it would be in the relational world if you indexed every column needlessly. So in most cases, it's actually recommended to leave the policy alone and let every property get indexed, even if you don't frequently query on it. But if you have very large documents with many, many properties, the vast majority of which you never query on, then you can shave off, you can shave off those RUs and get better performance and lower the RU charge on the writes if you define a custom policy that excludes those properties. But then you won't be able to query. I mean, you can then your query, if you attempt to query on those non-indexed properties, it'll pay a very big price for a sequential command, right? But it is possible.
Excellent. And finally, change feed, which I love the sound of. It didn't used to support deletes. I know that that's coming, but is it here now?
No, it's not here now, but you know it's coming, so you know. but there we have ways around it. Time to live is one way, and we'll see that in our next session.
Okay, fantastic. All right, thank you very much, Lenny. I really enjoyed the session.